Welcome to today's mini lecture. Today we are going to focus on looking at how the mole map and how using percent compositions can allow us to mathematically determine the formula for the compound. So what I'd like to first do is just show you the relationship between your percent compositions. So I have the problem in your notes, and it says determine the percent composition of calcium oxide, CaO. So to do that, I would just simply say calcium, and I know that calcium's molar mass is going to be 40.1. I know that oxygen's molar mass is 16.0. So that gives me a total for 56.1. So this is going to be the molar mass of one calcium and one oxygen. So I'm going to change pens so that y'all can see just a little bit better. The next thing that I want to do is determine the percent of each one. So I just say the percent of my calcium is going to be part, which in this case is 40.1 divided by 56.1 times 100. So guys, when I do that math, I come to find out that the percent is going to be 71.48%. And that's going to be calcium. So to do the oxygen, I just simply say the percent of oxygen is the part, 16.0 divided by the whole, 56.1, multiply that by 100, and I find out that my percent of the oxygen is going to be 28.52. All right, so I have that much so far. So the next thing I want to do is I want to do a percent composition of a compound. This is true, actual experimental data. And it contains calcium and it contains oxygen, but this time instead of giving the formula, I don't know the formula, but I do know that I had 10.73 grams and 4.28 grams. So I know that if I add those two together, I will get the total. So 10, I'm just going to do it right here, 10.73 plus the 4.28, I get 15.01. So, part divided by whole. Percent of my calcium, 10.73 divided by 15.01. Multiply that by 100. I find my percent of the calcium to be, and when I do it mathematically, I get 71.48%. So let's do the oxygen. Percent of the oxygen is 4.28 divided by the 15.01 times 100, and I find that this one is going to be 28.51%. Now the next question says, on your notes, it says, are the percentages the same? And really and truly, they are. We do have one small discrepancy right here. It's 5.2 and a 5.1. But guys, when you are using experimental data and you get to the hundredths and you're only off by one, yeah, that's pretty doggone close. We can use that. So it is the same thing. Why are the percentages the same? Well, what we find out is those percentages are based on percent by mass of the compound. Well, if you are using actual experimental data and you're collecting the mass of it, you're collecting the actual masses, they have to be the same ratio. So therefore, it's always going to be the same percentage. Now, if we know that, we can take this and go one step further. So what I would like to do is to work two problems. The first problem, they give me the molar mass and percent composition. The second problem, they only give me my percent compositions. Both of these are asking the same question. Can you determine what the chemical formula is going to be. So what we're going to do is we're going to go back, we're going to start putting all of this together. So in this one, I know that I have a total molar mass of 76.02. Well, if I know that 76.02 is the mass of both my nitrogen and my oxygen, and I know that I have the percentages of nitrogen and oxygen, I can determine what mass of that 76.02 is made up of nitrogen and what's made up of oxygen. All I have to do is say 76.02, and I'm going to multiply that by 369. And this is going to be my nitrogen. So when I do this, I'm going to get a number that's 28.01. So that's how many grams of nitrogen I get out of the 76. So let's do the same thing for my oxygen. I have 63, I'm sorry, I'm going to start with the molar mass, be consistent. I have 76.02. This time I'm going to multiply it by 63.1%, and that is of oxygen. But this time I'm going to get 47.987 grams of the oxygen. You say, well, what does that mean? Well, guys, we know that these ratios of the masses are going to have to be related to how many atoms we have. Well, how is it related? Well, if I know I have 28.02 grams of nitrogen, how many atoms would that be? Well, to figure that out is I just simply say I have 28.1 grams. I know that one nitrogen, by looking at the periodic table, is 14.0. That works out to be 2. I come over here and I say, well, how does this one go? Well, 47.987 divided by, it's the total number of grams of oxygen. I know one oxygen is 16.0. That would be 3. So what does that tell me? It tells me that my formula is N2O3. You're exactly right. It is pretty easy. You just have to make sure that you follow the steps. Now, we didn't use any mole-mole ratios here. We just used the ratio of masses because the masses and the moles, those ratios are the same. Now, if I look at my second example, do you see how this one never gave me my overall mass? Well, if I never know what the overall mass is, I can't do this same procedure. I'm going to have to do something a little bit different. And this is called a mole-to-mole ratio. So what I'm going to do is I'm going to take my 11.2%, and I'm going to assume that my sample is 100 grams. So I'm going to say that I'm going to start with 11.2 grams of hydrogen. Could I use my mole map and change that grams to a mole? Absolutely. That's what we were practicing on all last week. We said, put what you're given in a factor label box. Well, what do you want to go to? Moles. So I put that in the top. What do I have to factor out? A gram. What is the relationship between a gram and a mole? Molar mass. What is the molar mass? The number of grams per 1 mole of whatever formula I'm dealing with. This is just a hydrogen. So I know, looking at my periodic table, it is 1.01 grams per 1 mole. So when I divide that out, I get 11.2. All right. So that gives me the first part of this. Second part, actually, it gives me 11 point, I'm just going to go 0.9. All right. So now let's do the second one. I have 88.8 grams of oxygen. I'm going to put it into a factor label box so I can determine the number of moles. I put the moles here. I put the grams on the bottom. This time, it's still molar mass, but I'm using oxygen. So I got to use the molar mass of an oxygen atom, which is 16.0 grams per 1 mole. So now when I take and I divide I divide 88.8 by the 16.0, I'm going to get 5.55 moles. So guys, what I've just done is I've just figured out my number of moles. But I don't write this down as 11.09 and 5.55, or else this is what it would look like. H 11.09 O 5.55. Yeah, you can't do that. You got to have whole numbers. So what we need to do is we need to say, let's make these numbers here whole numbers. You say, well, how do you do that? Well, it's called a mole-mole ratio. So I'm going to take the smallest one, which is the 5.55, and I'm going to divide everything by the smallest one. We know mathematically if you divide everything by the same number that it doesn't change anything. So 5.55 divided by 5.55 is 1. 11.0 divided by 5.55, guys, that's 2. Look how I got nice whole numbers. That's awesome. Now, all I have to do is say, okay, hydrogens, I have 2. Oxygens, I have 1. Look what we were dealing with the whole time. Just some good old water. So, quick little recap. In this mini lecture, I talked about the significance of percent compositions. Didn't matter if you used the formula and did percent by masses, or if you used experimental data and did the percent by the mass collected. You're always going to get the same thing. Why? Because they are going to have the same ratios as our formula ratios. So we can determine the formula 2 different ways. They will either give you the molar mass and the percentages, and you follow these directions. Or they will give you just the percent composition, and you follow these directions. So as you finish copying these problems down on your paper, then go ahead and post it in your notebook, and then I will have another mini lecture for you to go through. Thank you.